Hi, and welcome to my next installment in my algebra and pre-calculus video series. In this video, we're going to be talking about systems of linear equations. Systems of linear equations. Now, before we get into this topic, I have a couple of questions, actually 4 questions up on the screen. And these are referring all back to things we've already talked about in previous videos, previous things that we've covered. So the first question is, what is an equation? Right? An equation, it's a statement. Right? It's a declarative statement. It's just given in the language of mathematics that says, all right, there's an equal sign, this thing on the left and this thing on the right have the same value, have the same meaning. So think $1 is equal to 4/4. They have the same monetary value. So for example, here's an equation. 3x minus 2y has the same value as 12. So 3x minus 2y is equal to 12. Now, what does it mean to solve an equation? Well, to find a solution, find an answer. Okay, what does that mean? What is an answer? What is a solution? Well, question number 2, what is a solution to an equation? When we're solving an equation, we're looking for truth, true statements. So a solution is a number or a set of numbers. Sometimes the answer has one part or one component. Sometimes the answer has multiple components, um, such that when you substitute that back into the equation, you get a true statement. All right, so what I'm looking at here is if x is equal to 6, that goes in for x, and y is equal to 3, and that goes in for y. We get 3, so I'm over here now, we get 3 times 6 minus 2 times 3 equals 12. Is that a true statement? Yes or no? Well, 18 minus 6 is equal to 12. Yes, check. That's a true statement. So the x equals 6, y equals 3 is a solution. Not the only solution, but it's a solution. Because when you take those two numbers and you plug them in for the x and the y, you get a true statement. Now we've also talked about graphing. We've also done a lot of graphing. Not just linear functions and linear equations, but we've graphed all kinds of different types of functions. Linear, quadratic, uh, polynomials, rationals, graphs, no matter where they're coming from, are always made up of points. Well, what is a point? Well, in the context of this word, equation, when you have a graph that represents an equation, it's made up of points. Now, question 3, what is a point? A point is a solution to an equation, right? We're not graphing functions here because functions don't have solutions. But when we're graphing an equation, a point is a solution to an equation. And that equation must have two variables. Because if it's going to be a point on the plane, on the xy plane, that means each solution is given as an ordered pair. Each solution is given as an ordered pair. So this from part 2, this x equals 6 and y equals 3 can be written as the ordered pair 6 comma 3. Okay, so this is not new. I'm going through this rather quickly because all of these items have been covered in thorough detail in previous videos that I've made. I'm just sort of reminding everyone of some important sort of conceptual sort of foundational points. And what is a graph? Well, a graph is a picture, right? A picture of what? A graph is the picture formed when every possible solution to an equation is graphed as a point, right? So every possible point goes on the xy plane, and together, collectively, they form a graph. Okay? Every point on the graph is a solution to the equation. Okay, now that we've got a little bit of review out of the way, let's talk about linear equations. So we're still sticking with equations. right? But let's talk about linear equations. A linear equation in two variables is an equation where the x is raised to the first power and the y is raised to the first power. There's no x squared, x cubed, square roots of x, y squares, no exponents other than 1. No x's or y's in the denominator of a fraction. Right? X to the first power, y to the first power, and an equal sign. If it's got those three, we call it a linear equation. Well, to be technical, the x and the y, we can't multiply them together. It has to be separate terms, but assuming that's true. So here's two examples. The green one on the left, that's a linear equation. And the blue one on the right, that is a linear equation. Each equation has two variables, which means each equation has infinitely many solutions. And we've already talked about what these graphs separately should look like. If we graph the green equation, we should get a straight line. Right? The graph of any linear equation is a straight line. If we graph the blue one, we should also get a straight line. So far, I haven't mentioned anything new that I haven't covered in previous videos or previous discussions. But what we're going to be talking about today in this video, this is the new part, this word systems of. Systems of linear equations. Well, we've already talked about linear equations, so it's not going to be all new. Okay. Each of these equations has a graph, right, as I've mentioned, right? The green line on the left is a picture of basically all of the solutions to that green equation. And the blue line on the right is a picture of that blue equation, well, all solutions of that blue equation. Now, every single point on the line is an answer, is a solution from the equation that it came from. Right? The equation comes first and the graph comes second, right? The graph is the answers to the equation. So we could label a handful of points, a handful of solutions. So there's five solutions to the green equation. Each one of these ordered pairs. Each one of these ordered pairs. Like x equals negative 12, y equals negative 1.5. If you plug those numbers in, you'll get 12. X equals 10, y equals 4. If you plug those numbers in, you'll get 12. X equals 0, y equals 1.5. You plug those numbers in, you'll get 12. So every point on the line, not just the 5 I labeled, not just those 5, this is just 5 examples, but there are infinitely many points on that green line. Each one of them is a solution to the green equation. Similarly, on the right, there's 5 examples of solutions. Each of these ordered pairs, plug those numbers in for x and y, you'll get a true statement, right? Any one of those points. Again, this is 5 of them. There are infinitely many more. Okay, do you notice anything between, if you look to the left and to the right and back to the left and back to the right, do you notice anything? Well, I'll give you a hint. I'll put a red box around it. You see the same point. You see the same point on both graphs. So that point, x equals 6, y equals 3, right? This is a solution to the green equation because it's a point on the green graph. This is also a solution to the blue equation because it's a point on the blue graph. So if I take these two equations and then I take these two graphs and I put these two graphs on top of each other. So let me go to the next slide. I think the next slide is where I do this. Let's just double check. Yeah, there we go. So now we've got the green graph with those 5 points I had labeled on the last slide. We got the blue graph, the same 5 points I have labeled, but the one that's on both, I made it red. Okay, that red point is the solution. That red point is the solution the only solution that works for both equations at the same time. We call that a simultaneous equation. So a solution to a system of equations, a solution to a system of equations, let me underline this, must be a solution to each equation simultaneously. So if you have two equations in your system, the word system means list. Right? That's all it is. A system of equations is a list of equations that we don't treat as separate equations, we treat it as one problem. So sticking with these two equations, for these two lines, we would say solve the system of equations. Now, this is one problem. This is one math problem. It has two equations, but the answer to this one problem is going to be the one solution that works for both equations. The one solution that works for both equations, and that's that guy right there. X equals 6, y equals 3. So if we plug a 6 and a 3 into the first equation, we get a true statement. If we plug a 6 and a 3 into the second equation, we also get a true statement. So the solution to this, again, to this system, the blue equation coming from the blue line or associated with the blue line, the green equation associated with the green line, the solution is the point 6 comma 3, or you could say x equals 6, y equals 3, either one. Either one is perfectly fine, either one is acceptable. Okay, so this is what it means to solve a system of equations. Solve a system of equations. So let me go to the next slide. This means one of two things. You could think about the solution in terms of the equations, or you could think about the solution in terms of the graph. A graph is a picture of the solutions. So both of these statements mean the same thing. To solve a system of equations means to find a solution that works for each individual equation, or you could say it another way, means the same thing, to find a point where the graphs of all equations intersect. In this video, the all equations is going to be two equations, right? But it doesn't have to be two. We could have a system of 3 equations, 4 equations, 10 equations. It doesn't have to be two. It doesn't have to be two variables. It could be equations with 3 variables, x, y, and z, or 4 variables, w, x, y, and z. In this video, we're dealing only with 2 equations and 2 variables. But again, this is just a specific, a specific case. There's no reason we have to be limited to 2 equations and only 2 variables. So I've just sort of been referring to the solution to the system as the point where the two graphs intersect. Well, it's not always as straightforward as that, because if you take two lines and you put them on the same xy plane, they don't necessarily have to intersect or cross in one point. Right? If you pick two random equations, two random linear equations, the most common thing to happen is that they intersect in one point. You get one solution. Right? This is the most common thing would be to see one single point of intersection, but it's possible that the system has no solution. We have two parallel lines. See that red line, that green line, they never cross. Right? They never meet. They're parallel. So there is no point of intersection. So if the lines are parallel, the system has no solution. So they could cross, meet at one point. They could be parallel and never meet. And then the third option, they could overlap. They could be two equations that maybe look different. But when you graph them, they have the exact same graph. So every single point is on both lines. I don't know if you could see in that graph on the right-hand side, but there's a green line and a red line sort of overlapping each other. There's two lines there, one red and one green. All right, so we could think about these as being special cases. I mean, once in a while you'll get a system with no solution. Once in a while you'll get a system with infinitely many solutions, but the most common is that the lines are going to intersect at one point. Okay, so graphing and looking at the graph, seeing where those two lines cross each other or intersect each other. I'm not saying intercept, that's something different. Intersect is one method. Solving by graphing is not the best method. It's not the best method. It works well when your graph, when your two graphs intersect at points that contain whole numbers, but it's very difficult to tell the difference on a graph between, you know, 1/2 and 13/25. They're different fractions, but they almost, depending on the scale of the graph, they're going to look like they're in the exact same place. So when you've got decimals or fractions, graphing just doesn't work. It's very difficult to read numbers off of a graph unless they're labeled, or if they fall on like the grid lines, let's say. So we're going to talk about two other methods. So down here, method 2 and method 3. They both always work 100% of the time. They're not completely separate methods. They're very related to each other, but it's two slightly different ways of doing the same thing. Use algebra, right? Use algebra to find the point where two graphs intersect without actually graphing. We don't have to graph every equation. We don't have to graph any of the equations. We don't have to graph any of them. But we're going to use a little bit of algebra to figure out, okay, if we were to graph these two lines and then look at the graph, where would they cross? Where would they intersect? Okay, so I'm going to go through an example of each. Let's do substitution first. And then the second one, addition/elimination. Some textbooks call it the addition method. Some books call it the elimination method, depending on what book you open up. So I'll just call it the addition/elimination method. They mean the same thing. We're going to eliminate something by means of addition. That's basically what we're going to do. So let's talk about method 2, substitution. Find the point where these two lines, the graphs of these two lines cross each other without graphing. So it's a 4-step process. But not every step always applies. Like, for example, in this problem right here, step 1 in a substitution, step 1 is to pick one equation, it doesn't matter which one, and isolate one of the variables. So you can solve the first equation for x, you could solve the second equation for x, you could solve the first equation for y, you could solve the second equation for y. You just got to pick one. In this example, this very first example, it's already done for you. Right? X is by itself, actually on both of the equations. So step 1 is done. Now, it's called the substitution method because we've got equation number 1. Let me write it side by side. X equals 7y plus 5. All right. That's just the first equation, right? And then the other one I'll write over here. X equals 3x minus 7. Or 3y minus 7. So let's look at this, just this first equation. What does this equation mean? Well, it means the x and the 7y minus 5 are interchangeable. That's what the equal sign is telling us. It's like one of them is a dollar bill and the other one is 4 quarters. They spend the same way, right? So you could swap an x out and replace it with a 7y plus 5. You could take a 7y plus 5 and swap it out with an x, right? These two are interchangeable. So what we're going to do is take the 7y plus 5 and replace it for the x. And we could do this because 7y plus 5 is equal to x. All right, so one equation, you isolate a variable, and then you substitute that into the other equation. So equation number 2, the one on the right, instead of saying x equals 3y minus 7, we'll say 7y plus 5 is equal to 3y minus 7. This is our goal, not just with this method, but with the next one as well. Substitution method, the addition elimination method, either one you use, this is what you want. This is your goal. One equation with one variable. It doesn't matter if it's a one equation with only the letter x or one equation with only the letter y, one or the other. Doesn't matter which one. But this is what you want. One equation with one variable. Because when you have one equation with one variable, you can solve for one answer. One single solution. All right? So that's our goal. That's what we have here. So solve for y. Right? So now it becomes here's a equation, solve for y. We can subtract 3y from both sides of the equation, cancel off those 3y's from the right. All right, so we got 4y plus 5 is equal to negative 7. And let's get rid of that plus 5 on the left so we can subtract 5, subtract 5. Those 5's will cancel. We've got a 4y is equal to negative 12. We want y by itself. Divide by 4. Both sides, those 4's will cancel, and we have y is equal to negative 3. Y is equal to negative 3. So our answer, let me put it down here in the bottom left-hand corner. Our answer is going to be something, comma, negative 3. Remember, our answer's got to have an x and a y. It's a point. It's a point, x comma y. So we just found the y. It doesn't matter which one. One of them you find first, one of them you find second. Doesn't matter if you find the x first or the y first. So now that we have y is equal to negative 3, we could go back to the original problem. We no longer need the letter y. We could plug in a negative 3 wherever you see the letter y. And so we're going to take that first half of our answer and substitute it. It doesn't matter which equation. I'll just use the first one because it's first. Makes no difference. But we're going to plug in a negative 3 for y. We're going to plug in a negative 3 for y. So x is equal to 7y plus 5. Well, y is now -3. Remember, these variables, they are temporary placeholders for numbers. Temporary is the key word there. We use the letter x and y until we figure out what x and y is. We figured out what y is. Y is -3, so we can replace the y with a -3. All right, so we got x is equal to 7 times -3 is -21 plus 5. So we get x is equal to, well, we got -21 and a positive 5, so that's a -16. So x equals -16, y equals -3, or we could write it as the point -16, comma 3. And that would be our answer. Now this is the substitution method. Some of my students only use substitution because they like it better. Some of my students only use the elimination or addition method, which I'm going to do next, because they like that better. There is no best method. And then some of my students use both. Sometimes, depending on the problem, sometimes substitution, sometimes addition, elimination. It's completely up to you. Substitution works. Substitution works. So I'll say works 100% of the time. It always works. 100% of the time, substitution works. Now let me move on to the next slide. So I did one problem with substitution. Now let me use one. So in this method, we're going to do the same thing. We're going to solve the system of equations. Find the point where these two graphs intersect each other without actually graphing. In this method, some books call it elimination, some books call it addition. I'm calling it the addition-elimination method. The first step is to pick one. Pick one of the variables to eliminate. It doesn't matter which one, but you're either going to focus in on the x's and say eliminate the x's, or you're going to focus in on the y's and say eliminate the y's. It doesn't matter which one. You just have to start off by deciding which one to eliminate. Now, sometimes there's a better choice. Sometimes the x is easier or the y is easier, but not much easier. It's not going to be a huge difference. It'll be slightly less complicated, very slightly less complicated to do one than the other. So for this example, I'm going to focus only on the x's. Eliminate the x's. Now, the way we do that, we'll look at step 2. Step 2. Multiply one or both of the equations so that the coefficients of the variables that you want to eliminate are equal but opposite. Okay, what does that mean? Well, let me ask you a question. What is 4x plus -4x? 4x and a -4x, when you add them up, you get 0. What is a 13x plus a -13x? You get 0. 1/2 x plus a -1/2 x, you get 0. All right, so when your coefficient, the coefficient, that's the number in front of the variable, right? That's the number in front of the x. So the coefficients for this problem on the x's are 8 and 4. It's 8x and 4x, so those are the coefficients. Now, when you're taking two things that are equal but opposite in sign, and you add them up, you get 0. And that's the basis of this entire method. You want them to be equal and opposite. Think equal and opposite. This is the method I prefer. I like this method better than substitution. That's just my preference. Right? Some of my students like one, some like the other. Now, right now, we don't have equal and opposite. We have a positive 8x and a positive 4x. They're both positive. Also, they're different numbers. One is an 8, one is a 4. So we need them to be equal, but opposite in sign. So what I could do is I could take the entire second equation and multiply it by -2. I'm only focusing on that part that's highlighted yellow. The reason I'm using -2 is because -2 times 4x will give me -8x. All right, so then I'll have a positive 8x from the first equation and -8x from the second equation. All right, equal and opposite. Okay, so let's write this out. The first equation I'm not changing. The first equation stays 8x minus 4y is equal to 44. But the second equation, I'm just changing what it looks like, not what it means. These are equations. We're allowed to do whatever we want as long as we do it to both sides. So we'll multiply everything by -2. Right? -2 times that, -2 times that, -2 times that. We get a new equation. So that will be -8x minus 20y. Oh, sorry, not 20. What am I doing? Minus 10y. -2 times 5 is 10. And then a -2 times a -13 is a positive 26. This is what we want. Equal, but opposite. Now, some books call it the elimination method because we're eliminating a variable, but also the substitution method eliminates a variable too. So that's a little misleading. Some books call it the addition method. The reason some books call it the addition method is the next step. The next step is add. Eliminate by addition. All right, left side plus left side equals right side plus right side. We have a positive and a -8x, so they give you 0. Got a -4y and a -10y, so that's a -14y. And then 44 plus 26 is 70, and we're one step away from half of our answer. Divide both sides by -14. So we get y is equal to -5. Y is equal to -5. Well, there's half of our answer. We know our answer is going to be a point. And the y value is -5. Let me get rid of some of this line because I need a little bit more board space. Okay, so how do we get the other half of our solution? How do we get the x? Well, we could repeat this process. We can now focus in on eliminating the y and keeping the x. That's one way. Or we could take that y equals 5 and plug that in. Remember, what is a variable? A variable is a temporary placeholder. Keyword is temporary. It's a temporary placeholder. So if we look at that first equation in our original problem, 8x minus 4y is equal to 44. Well, we no longer need the variable y. Why, you may ask? Well, we know what y is. It was a temporary placeholder. Now we know it's equal to -5. So we're basically taking the -5 and we're placing it in for the letter y. All right, so 8x, that's going to be plus 20. -4 times the -5 is a positive 20 equals 44. Subtract 20 from both sides. This is something we've done many, many times in previous videos, solving one equation for one variable. 24. Last step, we'll divide by 8. Divide by 8. The 8's will cancel, and we get x is equal to 3. And that is the other half of our answer. Down here on the bottom left, we have the point 3, -5. Now, let me go through this one more time very quickly. I'm not going to do the whole problem again, but I'm about to erase what's on the screen right now. All except the answer. We're going to keep the answer. But I'm going to go ahead and get rid of all of this work. And I want to go back to something I said at the very beginning, step 1. It doesn't matter which variable you eliminate. You just got to pick one. So I started off this problem by highlighting the 8x and the 4x and said, okay, I'm going to eliminate the x's. I could have started off by highlighting the y's and saying, I'm going to eliminate the y's. But in this case, if we want to restrict ourselves, only use whole numbers, right? If we don't want to bring fractions into the mix, well, we can't multiply 4 by something to get 5. We can't multiply 5 by something to get 4 unless we're going to use fractions. But to avoid using fractions, we can multiply both equations. We can multiply both equations. So equation number 1 will multiply by something. Equation number 2 will multiply by something. Now, what do we multiply by? Well, if we can't make a 4 out of the number 5, we can't make a 5 out of the number 4, we got to change both of those numbers into something common. Something common, right? Common multiple. Yeah, think least common multiple. So multiples of 4, 8, 12, 16, 20, 24, multiples of 5, 10, 15, 20. You see 20 is on both lists. 20 is the least common multiple. And you don't necessarily have to write out all of the multiples to figure that out, but we could use 20 as the least common multiple. So I can't turn a 4 into a 5 without fractions. I can't turn a 5 into a 4 without fractions. So if I'm only using whole numbers, I could turn them both into the number 20. So if we take the first equation times it by 5, that will give us a negative 20y. Take the second equation times it by 4, that will give us a positive 20y. So then, if we do what we did before, the entire first equation multiplied by 5. So that'll be 8x times 5. So that's 40x minus 20y is equal to 220. And then the second equation will multiply by 4. So that's 16x plus 20y is equal to, let me just make sure I get this right, 52, negative 52. Well, there's our equal and opposite. So when we do this, my red pen. When we do this, when we add these two together, these two equations together, left side plus left side, the y's will cancel. The y's will cancel. So on the left, we'll have 56x. And on the right-hand side, we'll have 220 minus 52 is 168. And if we divide both sides by 56, we get, no surprise, x is equal to 3. We already knew x equals 3 was the answer. So I did this same problem twice, or at least half of it the second time. Just to emphasize that it doesn't matter which variable you eliminate. Just pick one. Get that one to be equal but opposite in value in terms of the coefficients. Add them together, something will cancel. Okay, if you think back to that slide where I had those three graphs up, the two lines that crossed at a point, the two lines that were parallel, and the two lines that were overlapping. Well, the no solution and the infinitely many solutions, I said those are two more or less special cases because they don't happen very often. So let me just work through an example of each one. And you don't have to go into the problem knowing ahead of time that it's going to be no solution or infinitely many solutions. You just start it like any other problem, and then something interesting happens. Okay, so let's move on to slide 17. It'll be two to go, two slides to go. So in this example, I tell you ahead of time, here is an example of a problem with no solution. But you're not going to, when you're doing the homework, for example, or taking a quiz or test, you're not going to know ahead of time that the equation has no solution. So let's see what happens here. I'm going to go ahead and solve this by substitution. Substitution, it works pretty well when at least one equation has somewhere in your system, there's one equation that has a coefficient of 1, either a 1x or a 1y. So I'm going to take that first equation. Let me put on my pen. I'm going to take this first equation, which is 6x equals y minus 8. I'll solve for y because it's pretty easy to do. It's just one step. If we add 8 to both sides, the 8's cancel on the right. So now I have y is equal to 6x plus 8. So that means anywhere I see a y, I could replace it with a 6x plus 8. So I'm going to go ahead and take the 6x plus 8 and put it in for the y. So then that second equation, now instead of 6x minus y, I'm going to have 6x minus what y is equal to, which is 6x plus 8. Okay. So now solve for x. Solve for x. Now we could distribute that minus sign outside of the parentheses. So that's going to be 6x minus everything inside the parentheses. So minus a 6x and minus an 8. And on the other side of the equation, we have 1. Well, what's happening here? 6x minus 6x. They cancel. So we get negative 8 equals 1. That is a false statement. Negative 8 does not equal 1. Negative 8 does not equal 1. Not at least in this number system. Eventually, if you take a course where you're doing what's called modular arithmetic, then sometimes negative 8 does equal 1. But for our normal, when I say normal, I mean our everyday number system, negative 8 is not 1. Negative 8 is negative 8. 1 is 1. They're two different numbers. So if you put an equal sign between them, that is a false statement no matter what. Under any circumstances in the real number system, under any circumstances, that is a false statement. If you hit a false statement, you stop there. The answer to this question, to this problem, solve the system of equations. The answer is no solution. If you take those two equations and you put them into your graphing calculator, or you type them into Desmos or some other graphing utility, you will see two parallel lines. They are parallel lines. They never meet. They never cross, which is why when we try to solve for the point of intersection, we get this weird contradiction, this false statement. So when you hit a situation where all the variables cancel off, the x's cancel, the y's cancel, and you're left with an equation that is just not true, -8 equals 1, that's no solution. That system has no solution. Now, last one I want to do, solve the system by any method you prefer. I think in this one I'm going to use elimination. So let's eliminate the x's. All right, 2 and 4. So 4 is a multiple of 2, so I can multiply the first equation. I can multiply the first equation. Oh, I've been using red for my steps. Multiply the first equation by -2, because that -2 times 2x will give me a -4x. And that will cancel the positive 4x on the bottom. Right, equal and opposite. Okay, second equation stays 4x plus 10y is equal to 6. But the first equation, -2 times everything. So that becomes a -4x. So I want to eliminate those x's. All right, but then -2 times 5y is a -10y. And then -2 times 3 on the right side is a -6. So, when we add these two equations together, -4x and positive 4x cancel, -10y and positive 10y cancel, -6 and positive 6 cancel. Everything's canceled. We have 0 on the left, 0 on the right. 0 equals 0. That is always true. Under any circumstances, 0 is equal to 0. So that means there are infinitely many solutions, but we have to be a little bit more specific, okay? If it's no solution, you just say the words, there is no solution, or just no solution. That's the answer. If there's infinitely many solutions, we can't just say infinitely many. We have to be more specific, because it's not every single point in existence. It's only the points on the line. Now, these two equations have the exact same graph. If you graph the first one, graph the second one, they're going to overlap each other. So the final answer will be, we're going to use what's called set builder notation. The set of. So that's what these curly squiggly brackets mean. So when you open a bracket using this type, that means the set of ... whatever comes next, the set of something. So it's going to be the set of all points x comma y, such that. So that vertical line means such that. Let me write that down here. We've seen set builder, but it's been a while. Let me use another color here. Such that. I'll use orange for the annotation in terms of the symbols. So the squiggly bracket, the set of, now we've got points, x, y, vertical line, such that, and then just copy the problem. Pick one equation. Those two equations have the same line, so it doesn't matter which one you use. So the set of all points, such that 2x plus 5y equals 3. So we're not really doing anything here. We're just taking the problem and we're putting it into set builder notation. Right, so this would be this would be the answer. Or use the second equation. Doesn't matter. The set of all points x comma y such that 4x plus 10y is equal to 6. It doesn't matter which equation you use. Just copy one of the equations into your answer. You could use either one because they have the same graph. They have the exact same graph. Okay, so that is it. We did one example of substitution. We did one example of elimination. Then we did one more example of substitution where there was no solution. One more example of elimination where there were infinitely many solutions. I'm going to stop the video here. I'll pick it up in part 2 of this video where I'll continue on with my notes, but in part 2, we're going to use the substitution and elimination methods to solve word problems. So part 1 of the video, solving the equations. Part 2, we will look at specific types of word problems. All right, that's it for now. I hope this was helpful.